Hello, and thank you for joining us. Today's webinar is Selection and Sizing of Thermal Mass Flow Meters and Mass Flow Controllers, presented by Doug Baker, Director of Sales and Business Development for Teledyne Hastings. This webinar is being recorded and will be available within a few days. Okay, now I'll turn it over to Doug.
Hey, thank you, Shelley. Hello, and welcome to today's webinar. And so in this webinar, we're going to discuss the various factors that determine the size of a flow instrument, as well as things that you may want to consider when selecting a flow meter or flow controller. And first, a little bit of housekeeping. As Shelley mentioned, this webinar is being recorded, and copies of the recording and the slide deck will be made available to all attendees. Also, please note that previous webinars for both flow and vacuum topics are available on our website. So we invite you to check those out. You simply go to the Resource Center of our website, and then you click on webinars. My name is Doug Baker, and I am the Director of Sales and Business Development here at Teledyne Hastings, located in Hampton, Virginia, USA. And I welcome your feedback and questions, so please feel free to email me at dbaker@teledyne.com. Let's get started. We're going to start the webinar with a quick review of the basics of a thermal mass flow meter. We will introduce each of the key components so we can understand how we build up the instrument and get the sizing right. We're going to introduce the idea of nitrogen equivalent flow and how we use that number to give us the correct gas line size, flow instrument body, fittings. We'll also discuss some of the other considerations for selection of a thermal mass flow meter. Then we're going to move on into the components and operation of mass flow controllers. And we're going to discuss how we size the valve of a mass flow controller to ensure that we get the best performance for a given application. And just like for our discussion on flow meters, we're going to touch on some other consideration factors for selection of thermal mass flow controllers. And then we'll conclude with a list of resources that are available to you. So I mentioned that we're going to build up a thermal mass flow meter. So let's start with a cutaway of a simple flow meter. The gas is going to move from left to right in the stainless body at the bottom of the picture. In the back, we see the electronics card, but what I want to draw your attention to is the insulated black square in the middle. This is the actual flow sensor, and there are two small ports at the bottom of the flow sensor that allow gas flow into and out of the flow sensor. Now, if we peel away the thermal insulation, we would find a small diameter capillary tube in the shape of an arc. Again, gas enters one end of the arc and then exits out the other end and back into the flow body. Now, on the outside of the arced capillary tube, there's going to be some sort of heater winding or combination of windings and some method to detect the temperature. Now, there are various thermal mass flow sensor designs. I've shown three configurations here, but I'd like to focus on the basic constant temperature heater design. Conceptually, it's pretty easy to follow. In this design, a central heater winding takes the center of the tube up to a constant temperature. Now, there are two thermocouples, you can see them there, the one on the left, TC1 and TC2, and those are placed symmetrically away from the heater. As you can see from the arrows, flow enters from the left and exits out the right. Okay, let's look at what happens when there's no gas flow through the sensor tube. Now, TC1 and TC2 are going to come up to the same temperature, right? They're located symmetrically away from the heater, so they're going to come up to the same temperature. But as flow moves through the tube, molecules carry thermal energy away from TC1, and then you have heated molecules from the middle that carry thermal energy to TC2. So what's going to happen is TC1 is going to cool down, TC2 is going to heat up. The net result is you get a temperature difference between TC1 and TC2 that is proportional to the gas flow. Now that we've seen the inside of the flow sensor, let's go back to that cutaway view. As you can imagine, most of the flow moving through the meter never actually passes up through that sensor tube. Only a portion, typically about 10 cc's, I should say 10 standard cubic centimeters per minute or so, actually makes the trip through the heated sensor tube. There's a component called the bypass shunt, which determines the ratio of flow between the bypass and sensor. The shunt is important. It determines the full scale range of the flow meter. A well-designed shunt forces the gas into laminar flow such that the flow is well behaved. The flow is often conditioned at the inlet to avoid turbulence. Now you see the shunt at the bottom right there has small corrugated passages to ensure the laminar flow. So there are many different shunt sizes, but no matter what size, the role of the shunt is the same. It will give a pressure drop across such that the sensor has about 10 standard cubic centimeters per minute or so near full scale as flow passes through the body. Of course, larger shunts require larger flow meter bodies and fittings and line sizes. So for your application, we want to ensure that we select the correct shunt and corresponding flow meter body to provide the desired full scale for the flow meter. And as you can see from these pictures, we have a broad range of models with various shunt sizes available. And we also manufacture laminar flow elements, or what we call LFEs. In these pipes, as shown here, there are corrugated passageways to ensure well-behaved flow. As flow travels through the pipe, some of the flow passes up through the thermal mass flow meter that's mounted there via elbow fittings, and in turn, a fraction moves through the heated capillary flow sensor. So we can reach some very large flows. In fact, the meter shown on the far left there features an 8-inch flange, and that meter can measure flow up to 15,000 standard liters per minute of air. And then our LFEs, they can be shipped with pipe thread terminations, smooth, where they can be welded into other pipes, or flanges where they can be bolted into systems. And now is a good time for me to point out that here at Teledyne, we have the infrastructure and flow standards to handle very low flows all the way up to some very large flows. And the digital 308 shown in the lower right-hand corner there will measure and control flow accurately up to 10,000 standard liters per minute. Okay, you've seen pictures of all these various sizes of flow meters. Now, how do we know which size is right for a given flow rate? Well, all of our models are referenced to what we call nitrogen equivalent flow. So when we look at one of our data sheets or manuals, we see that the meter can be ranged up to a certain flow rate. And what we are talking about is the range in terms of the response of the meter in nitrogen at so many standard liters per minute, at so many SLM. While we're not going to get into reference conditions for standardized flow rates, also known as STP, at least not for this webinar, we are going to need two things to determine the nitrogen equivalent flow in standard liters per minute. First, if we're working in units other than SLM, we're going to need a conversion for the units, say, to go from standard cubic feet per minute, or SCFM, or standard cubic feet per hour, SCFH. The other thing we're going to need is the gas conversion factor. This factor is required because gases other than nitrogen will transfer heat either more or less efficiently depending upon their physical properties. For example, methane, CH4, is more efficient at transferring thermal energy compared to nitrogen because it has more vibrational modes than nitrogen, or we say it has more degrees of freedom. But let's make this really simple. All you need to do is tell us what gas, what units, what flow rate that you need, and we'll provide the nitrogen equivalent flow in standard liters per minute. And then from there, we can select the body size and shunt that will be required. Okay, now that we know how to get at the correct size of flow meter, let's talk about some of the other considerations when selecting a model. We often work with customers that want to minimize the pressure drop across the flow meter. And this usually comes down to the method of flow conditioning that we use on the inlet side of the flow meter. For example, our LFEs, those laminar flow elements that I showed a couple slides ago, have only corrugated matrix passageways and offer minimal resistance to flow. Now, of course, LFEs should be installed properly with a nice long straight run of pipe. We usually recommend 5 times the diameter of the pipe upstream of the flow meter, and additional straight run of pipe, say 1x to 3x diameter on the downstream side. Some of our flow meters have sintered elements to set up flow into the meter, and those sintered elements also act as a filter to keep out contamination. So these are going to have a higher differential pressure, a higher pressure drop. So you might want to talk to us. We'll give you some options and discuss the pluses and minuses of each. Now, you may also need to consider the environment of the installation of your flow meter. If you're going into an outdoor setting, or maybe you have a splashdown environment or a really pretty dusty environment, you may want to consider an IP67 enclosure to keep out water and dust, that sort of thing. Now let's transition to mass flow controllers. And before we discuss sizing, we're going to touch on the valve operation. Of course, the only difference between a mass flow meter and a mass flow controller is the addition of a proportional control valve. So all mass flow controllers include mass flow metering. But it will be helpful here to isolate the valve conceptually so we can look at the key components. The proportional valve shown here uses a solenoid coil for control. An orifice located at the bottom of the valve is going to limit the flow rate for a given gas and set of pressure conditions. A Cal-Res elastomeric valve seat is used to seal off the orifice when the valve is to be closed. So the valve seat is attached to a spring, and that spring is preloaded to ensure the valve is closed when no current is passing through the solenoid. In other words, we say the valve is normally closed. That is, if power to the MFC is lost, the flow is stopped. Now, during valve operation, a control loop circuit located on the electronics card compares the flow signal coming from the flow sensor to the user's command signal. The control loop then supplies current to the solenoid to lift the valve seat up and off the orifice, which in turn allows flow to pass through the body of the valve. The control loop is constantly adjusting the current through the solenoid to maintain the flow signal at the desired command set point. The solenoid design shown here is very nice because there's no shaft to the outside world. The orifice, the valve seat, they're all inside a metal sealed valve body. And I'll point out that we helium leak check every flow meter and flow controller before it ships to ensure we're not introducing any leaks into your system. So now let's discuss the sizing of that orifice. Now, as you can imagine, this is important to get right. Again, the orifice is going to determine how much flow we can get through the valve. Now, I've shown a simple orifice equation here. It's valid only when the upstream pressure is greater than 2 times the downstream pressure. The diameter of the orifice, that's given in inches. That's what we're going to calculate. Sigma is the specific gravity of the gas. Q is the flow rate in standard liters per minute. And P sub U is the upstream pressure, and P sub D is the downstream pressure. Now, there are all sorts of factors that go into determining the optimal orifice size, and our application engineers are happy to discuss your parameters and specific details for you to be successful. We don't just pull product off the shelf. We configure the mass flow controller to get the best results. So we would ideally like to know the flow rate that's going to be required, the gas that's going to be used, the upstream pressures and downstream pressures, and then the application. It could be a downstream, you might have a downstream regulator, or it might be a fill application where the downstream pressure is slowly building up with time. In this image, we see the top of an orifice, and I also put in this picture a 1 mil diameter wire, so you can get a sense for how small these orifices can be. Okay, now let's talk a little bit about upstream and downstream pressures. In many installations, the user may have, say, a gas bottle upstream, or maybe they've got a compressor, that sort of thing that is supplying gas. They may have a pressure regulator preset to a known setting, and then sometimes maybe a filter. Downstream of the flow controller will often be some sort of process. Now, in our orifice sizing calculations, we can enter a range of pressures, both upstream and downstream. So we will usually ask the end user for their maximum and minimum upstream pressures, as well as the maximum and minimum downstream pressures. So even if the exact values are not known, we can enter some estimate for max and min to cover any uncertainty. Now, in general, there needs to be a pressure drop across the flow controller of at least 15% of the upstream pressure. Sometimes there may need to be more DP or pressure drop. Sometimes we can get away with a little less. The point is, we're here, you can talk to us. If low pressure drop is important, then we have extensive experience and we can help with that. And one other thing that I want to mention about pressures is don't worry if you don't know the exact values. It's not unusual. In fact, sometimes a little sketch on the back of a napkin showing your piping and elements in your flow path, that can go a long way for us to collectively understand how we can get to the best flow controller sizing for the application. Now, flow rates and pressures aren't the only things to consider when selecting a mass flow controller. And we're going to spend a few minutes drilling into each of the items that are shown here. Of course, we want to ensure that the process gas being used does not have any issues with compatibility. If there are elastomeric seals in the flow device, we want to select the right material. Maybe it's Viton, neoprene, Buna-N, Calres. We want to select the right seals that will work with the process gas. And it's not just O-rings that we need to consider. We may also find that we have other material issues that should be addressed when configuring the mass flow controllers. You also want to give some thought to how you want to interface to the flow instrument. If you're using a strictly analog mass flow controller, you will need to send a command signal and read back the flow rate. Now, many traditional MFCs operate using 0 to 5 volt DC input-output, but we also see a lot of 4 to 20 milliamp IO for folks with long cable runs and or if they have connections to PLCs. You may also want to consider going strictly digital IO via RS-232 or RS-45. We also have USB serial or Ethernet. Now, one of the advantages with the digital approach is that you can use our free software or you can use our free certified LabVIEW drivers. There's also an added benefit because with digital, there's no uncertainty in the steps going from the D to A to the A to D conversion with the signals. I also want to mention that we're happy to assist with wiring questions. We've seen a lot of things over the years, so we're happy to help with wiring up flow controllers to systems and power supplies. And for those who don't want to hassle with wiring, assembling cables, soldering the D connectors and all that, we have both a single channel, that's the THD 101 shown on the left, and a 4-channel THD 401 shown on the right. Those are power supply, controller, display units. We can provide cables, so you can simply connect power supply, that read out to the MFC, and you can get up and running. Or if you want the easiest of all, you can go with the 300 view line of flow meters and flow controllers. And these can be powered by simply plugging in a 24-volt power supply, as shown there on the left. And with a touchscreen display, you enter the flow rate, and the MFC takes care of the rest. And I'll also mention that all Digital 300 have both analog and digital I/O. So you see the top cover there shown on the left. Now, as you probably figured out, we really enjoy working with end users, and we have many paths for you to contact us. We have our live chat, which is available on our website, or you can call or email us. And if you want to have a more in-depth discussion about a flow or a vacuum application, we're happy to set up a quick Zoom meeting. And then in addition to our factory application engineers, we also have a global network of experienced sales channel partners who can help you with selection, sizing, pricing, and delivery. You can find your local technical and sales support on our website. And we strive to provide excellent service, not just on the phone and email, but also with our calibration and repair services. In addition to our factory staff in the USA, channel partners in Europe, China, and South Korea are available to provide global support for calibration and repair. And we also provide lifetime technical support. You can always call us. We're always here for you. If you have questions about measurement and control of gas flow or vacuum, or you want to discuss a new application, we are here to help. And finally, I want to thank you for spending some time with us today and listening to this webinar. And as I mentioned earlier, your questions and feedback on today's webinar are welcome. And I'd be honored to hear from you. You can reach me at dbaker@teledyne.com. Thanks again.